In this program, we're going to take a look at the equilibrium law expression and the equilibrium constant. I'm going to start by considering a reaction between hydrogen and iodide to make hydrogen iodide. We know that once we get beyond this point in time, the concentrations remain constant, and we've reached a state of equilibrium. At equilibrium, the rate of our forward equals the rate of our reverse reaction. You might remember from our rates unit, you can express the rate of the forward and the rate of the reverse reactions as follows. We have a rate constant times the concentration of hydrogen times the concentration of iodide for the forward reaction, the rate constant for the reverse reaction times the concentration of hydrogen iodide squared. I'm assuming in this case that both reactions occur in one step. I'm now going to isolate for the concentrations on one side and the rate constants on the other side. We can combine the rate constants to come up with what's called the equilibrium constant. And on the right-hand side, we have the equilibrium law expression. First thing about the equilibrium constant, capital K. You'll see a small c there, and that refers to the fact that we're using concentrations, and those concentrations must be at equilibrium. At any given temperature, the value of this constant can change because the rate constants from which it's derived can also change. So here I'm specifying at 425 degrees C the temperature, Kc is 50. In general, for any reaction that's of the form A plus B makes C plus D, with their appropriate coefficients, the equilibrium law expression looks like the following. Going back to the first reaction on the previous slide, in row number 1, I've placed all the information we have, the reaction, the equilibrium law for it, and the constant. In the second line, how have I changed the reaction? Well, it's the reverse reaction. So the equilibrium law expression would flip the top and the bottom. We would say they are reciprocals of each other. And in a similar fashion, the equilibrium constant would now be 1 over 50. In the third line, I've multiplied the second line by a half. The equilibrium law expression would look as follows. Remember that raising something to the 1/2 represents the square root. So what I've essentially got then for the equilibrium constant is the square root of 1 over 50. I'd like to introduce two types of equilibrium. Homogeneous equilibrium, which we primarily dealt with, and heterogeneous equilibrium. Here's an example of a homogeneous equilibrium, where everything is in the gas phase. Generally, reactions and products that are all gases or are all aqueous are usually considered to be homogeneous reactions. If we look at the start of the reaction with the presence of just A and B, and then we move to equilibrium, we can see that the concentrations of the species have changed. And I'm showing that here in a graph, green representing the product. We can then write the equilibrium expression then as follows. But notice in a homogeneous equilibrium, the concentrations of all of the species can change until we reach equilibrium. In a heterogeneous equilibrium, it's a little bit different. We have in this case a solid and a gas, two visible phases. We start off the reaction, in this case, with B gas and A solid, the blue down in the bottom left-hand corner. As this reaction proceeds, we move towards products, the concentration of the red gas changes, as well as the concentration of AB. But the concentration of the solid doesn't change. It essentially remains constant because the spacing between the particles remains the same. So it would look something like this. Generally, pure liquids and pure solids have constant concentrations and are left out of the equilibrium expression. So the equilibrium expression for this would ignore the presence of A. Let's try a question employing a couple of these ideas. First of all, see if you can determine what the rate law expression would be for this reaction. You notice here the presence of the solids. They wouldn't appear in the expression. In the second part of this question, you're told that the equilibrium constant for the previous line is 40. Here, I would like to determine the equilibrium constant for the reaction below. You'll notice that it's flipped. Reactants and products have switched sides, so I would then expect 1 over 40. But I've also doubled the equation. That means I'm going to have 1 over 40 squared. To finish off, I want to look at situations where I have large equilibrium constants and small equilibrium constants. Beginning with large equilibrium constants, they would have a high concentration of product and very little reactant. It's often said that the reaction goes near completion in these cases, and graphically it would appear as follows, where red is the reactants and blue the products. When K is a very small number, we have very little product and a lot more reactants. In such situations, we say the reaction hardly produces any product, and graphically it would look as follows. Again, red is the reactants and blue the product. Thanks for watching.